Imagine a world where your phone's signal remains perfect and reliable, even in the most crowded stadiums or bustling urban environments. What if a single base station could handle hundreds of users simultaneously, delivering lightning-fast speeds of gigabits per second to everyone without any drop in performance? This isn't science fiction, it's the reality of Massive MIMO, a groundbreaking technology revolutionizing wireless communication in 5G networks. But what exactly happens when a base station employs 128 antennas to manage all that traffic? To truly understand Massive MIMO, let's trace the evolution of wireless technology from the basics. Early cellular systems like 2G and 3G relied on a single antenna, known as SISO or single input, single output, at the base station. This single antenna broadcasted signals omnidirectionally in all directions, resulting in limited capacity and speeds of only around 10 to 20 megabits per second per cell, constrained by Shannon's capacity formula. Then came MIMO, or multiple input, multiple output, introduced in 4G LTE networks. This key innovation used multiple antennas in configurations like 2x2 or 4x4 to send and receive multiple parallel data streams simultaneously. MIMO dramatically boosted capacity by enabling these parallel streams to operate without interference, effectively doubling or quadrupling throughput through spatial multiplexing using channel state information, or CSI. But it gets even better with Massive MIMO, which scales this concept massively by deploying hundreds of antennas, such as 128 or even 256, in a single base station as supported in 5G NR standards. This massive antenna array can serve dozens of users, say 20 to 40, concurrently, achieving spectral efficiency gains of 10 to 25 times over traditional 4G, as proven in real-world trials like Nokia's 2016 Helsinki test. At the heart of Massive MIMO is spatial multiplexing, where each antenna in the array sends a unique, tailored signal to a specific user, separating them spatially through the air. The base station uses intelligent pre-coding techniques, like zero forcing or MMSE, exploiting multipath propagation to make each user's channel nearly orthogonal, effectively eliminating interference between signals. This setup allows serving many users simultaneously, typically K users where K is much smaller than the antenna count M, with capacity scaling as approximately K times log 2 of 1 plus times SNR. For example, M equals 128 and K equals 32. Complementing this is beamforming, a powerful technique that acts like precise energy focusing. Instead of wasteful wide broadcasting, the antennas concentrate their energy like a spotlight directly on each individual user. Digital beamforming achieves this by meticulously adjusting the phase and amplitude across the entire antenna array, dramatically boosting the signal-to-noise ratio through coherent power concentration. For a large array of 128 antennas, beamforming delivers a remarkable 21 dB gain, equivalent to 128 times more power, transforming a broad floodlight into a sharp, powerful spotlight beam. Massive MIMO unlocks its extraordinary high capacity by seamlessly combining spatial multiplexing for parallel streams with beamforming for SNR enhancement, working together synergistically. This powerful synergy drives massive throughput gains, with real-world examples like Verizon's 2025 G trials achieving 1 gigabit per second per user using 64 antennas, and Ericsson's 2023 demos showing 10x capacity over LTE. As a result, total cell capacity scales linearly with the number of antennas, enabling a 128 antenna system, or 128T128R configuration, to deliver over 100 gigabits per second in aggregate throughput. But here's the key insight. The true magic of Massive MIMO lies not just in the sheer number of antennas, but in the sophisticated signal processing algorithms that intelligently orchestrate their performance. Raw antennas alone are inert hardware. It's advanced algorithms like pre-coding matrices and conjugate beamforming that unlock their full potential through precise control. These complex algorithms process signals in real time at rates of hundreds of gigabits per second, powered by specialized hardware such as FPGAs and GPUs to handle the massive computations. It's this invisible computational wizardry that truly transforms a dense forest of antennas into a highly efficient, high-capacity wireless communication powerhouse. Massive MIMO was first introduced by Thomas L. Marzetta in his seminal 2010 IEEE paper, and it continues to evolve, with future 6G systems eyeing over 1024 antennas and AI-driven intelligent beam management. Ultimately, this technology is not merely about deploying more antennas. It's about creating smarter, algorithmically driven antennas through cutting-edge signal processing. If you found this deep dive into Massive MIMO fascinating, make sure to subscribe for more in-depth tech explainers and insights into the future of wireless communication like 5G and 6G.